Hello everybody, Adam Lusek here, and today we're going to be talking about static and distilled embedding models. Essentially, a few older techniques of using static-based embeddings, which we'll get into in a bit, have resurfaced with some modern updates to create embedding models that are both 400 times faster without losing a whole lot of quality. If you know anything about me, I've put a lot of time into optimizing the retrieval step of a retrieval augmented generation pipeline, which heavily relies on the embedding model. As a quick refresher, embedding models play a huge part in the machine learning ecosystem, allowing us to do things like textual similarity, semantic search, paraphrase mining. It's even the kind of models that are behind actually highlighting the piece of text in an article that's best to answer a question that you input if you Google it. They're pretty much trained through large corpuses of text and content to be able to take in some form of unstructured data. Generally, in our context, we're going to be working with something like text, running it through a machine learning based model, and then outputting a semantically rich representation in numbers of that data object. What that means is we're essentially converting something like text and natural language into numbers, and those numbers are going to capture the actual semantic richness and meaning of the text, which allows us to do things like mathematically compare how similar things are because we're now able to represent them as numbers. These kinds of models predate the large language model as we know it and are some of the original forms of language modeling that was actually very successful. We've seen advances with things like BERT or bidirectional encoder representations from transformers coming out of Google, pretty much revolutionizing this field. And some of the most downloaded models are embedding or encoder models like AllManyL ML6v2 here that boasts an impressive almost 83 million downloads a month. If you want to learn more of the specifics of exactly how things like BERT models and transformer models that do these sentence encoding actually works, I implore you to check out my other video, which I'll have linked right above here. But one of the core issues that's been identified with modern day embedding models like the lovely AllManyLM here is that there's still a roughly large amount of parameters. While relatively trivial in comparison to some of the 70 and 100 billion plus parameter models that we see with large language models, they can still reach pretty decent parameter sizings, which in turn means that you need some pretty decent hardware to be able to run large scale tasks on these kind of things. So today we're going to be looking at a few different efficiency gains that we can get using some older techniques with a modern twist with the static embedding models, and also showing how you can use an existing model and distill it down into a static embedding model itself to push the performance and efficiency of embedding models. But before we do that, a quick word from the sponsor of today's video. Brilliant. Brilliant helps you get smarter every day with thousands of interactive lessons in math, science, programming, data analysis, and artificial intelligence. A lot of people ask me how I stay on top of the ever-changing field of AI. And it's not by doing everything all at once, but rather learning a little bit every single day and applying what I know. With Brilliant, you can start to build those daily habits of learning something and applying something new every day. With just a few minutes, you can turn your mindless scrolling into actual productive time, jumping into useful and applicable topics for both your personal and professional life. One of the courses that I think is particularly beneficial is the Programming with Python course. It's something I use every single day, and Brilliant's newly updated programming courses are a great way to build a foundation in coding. Not only can you do things like get familiar with Python and start building programs from day one, but the more important thing is that Brilliant's course here helps you develop an intuition for computer logic. So not only will you learn strong fundamentals about programming, but also a little bit of how to get yourself in the mindset of a programmer. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/AdamLusek or scan the QR code on screen. Or you can click on the link in the description. You'll also get 20% off an annual premium subscription. Thank you to Brilliant for the sponsor. Now back to the video. So the first thing that we're going to go over is what are static embeddings. And to do this, we're going to look at one of the earliest, most popular static embedding models, W2V, which came out in September of 2013, which in AI years seems ages ago, and is a cool model that came once again out of Google. And so what Google showed is two novel model architectures for computing continuous vector representations of words from very large datasets, or essentially being able to take large corpuses of text and training a model to be able to effectively represent the text as numbers. And so while this idea of encoding and representation is shared across both static and dynamic contextual or transformer-based embeddings, what the actual core difference between static and the more popular these days transformer-based embeddings are is that static embeddings are going to be a predefined per token level embedding. Jumping down to a couple of diagrams here to show exactly what we mean here is that the advantage that the transformer-based embedding model has is that it's able to use, of course, the attention mechanism to be able to give more contextual meaning to specific words. So every time you actually encode a sentence, each one of the words in the sentence is going to be considered as it relates and correlates to every other word in the entire sentence. This can highly change the actual definition and meaning of the word. Looking at something like, I have no interest in hearing about the rising interest rate of the bank, we can see that interest here means something more like desire or intrigue, whereas the second interest means more monetary and physical. Now, the beauty of the transformer and attention mechanism within some of the more modern approaches here is that we can very granularly identify the different meanings of this word interest as it relates to everything else in the sentence. So it's very contextual and dynamic. Static, on the other hand, is going to have one assigned embedding for every single individual word or subword token level. So rather than calculating the entirety of the representation of the sentence every single time, we're essentially going to be creating a lookup table where each word or subword is going to have a corresponding vector that's learned through the mass scale machine learning on a large corpus of text. How does this happen? Well, we can look at the two specific ideas that the Google paper introduced: continuous bag of words, or from now on I'll just say SIBO, and skipgram. These are essentially going to be training objectives, where the model during its training is going to be trying to do a specific task. And through this task and through many, many thousands and millions, if not hundreds of millions of examples, is going to learn how the actual human language works to be able to do this representation accurately. So for something like skipgram, what we're doing is going to be predicting the surrounding words in a context window given a center word. So for the example of a context window of 3 and the sentence, the quick brown fox jumps over the lazy dog, if we look at this middle example here and have the word fox, the predicted words that we would want are the quick brown and jumps over the. Or for something like the at the start, we would want to predict quick brown fox. And then continuous bag of words is a little bit of the inverse of skipgram, where given the surrounding words, we are going to predict the center word. So given the quick brown jumps over the, we would want to predict fox. Now, if you're unfamiliar with how kind of, machine learning and language models are trained like this, what's going to go on is many thousands and millions of these examples are going to be shown to the model. The model is going to be trying to predict either these outside words if using a skipgram model, or the inner target word given the continuous bag of words approach. And what's going to happen is that the output from the model, which might be something like quick brown fox in comparison to the when this is ran through, are going to be compared to the actual expectation and the ground truth. And then given the accuracy of the model to actually be able to do that prediction, what we're going to do is update all of the inner numbers or the weights and biases within the model to maximize that accuracy. So over time, the model will become better at actually doing this specific task. And if we look at something like languages here, that means that it's going to build a better internal understanding of language or be able to model language. Thus, using these kind of fill in the blank or predict around approaches to training language-based models can help actually instill and generalize over the many millions of examples that tend to be shown to actually have some sort of inherent understanding of how language works. Pretty much because you're able to understand what words go where. These two approaches are not the only ones that have been used to train static embedding models. We've also seen the idea of word co-occurrences and frequency pop up. Things like the glove model or global vectors for word representation coming out of Stanford use this co-occurrence matrix in an interesting way, which essentially posits that words tend to be grouped together. And in training with something that follows a occurrence or frequency based approach, we can capture that distribution of semantics of language based on kind of this specific principle. Now, before we actually show some of these static embedding models in action, I do want to talk very quickly about the act of tokenization. Tokenization plays a very big part in this because essentially it's going to create what is known as the vocabulary for these models, or the entire range of different words or parts of words or combinations of characters that are going to be learned and understood over this training process. It's likely that you're familiar with tokenization because of how it applies to language models. We're taking raw text. Essentially, it's going to be split into all of these individual components. So something like many is going to be one token, but then this space and words is going to be another token. And it's going to take an entire sequence here and essentially chop it up into individual pieces. These, of course, do not usually take the form of just plain characters like this. Rather, they become the numbers, and then these numbers correspond back to the specific text so that in the life cycle of actually interacting with something like a language model, if you input a prompt, maybe it's something like this, it gets converted to numbers. Those numbers are then input into the LLM, which is then able to be calculated and do the next token predictions. And then those next predicted tokens from the language model are then mapped back to the text to give us our plain English, or any language for that matter, output. Now, this plays a part because essentially every single one of those tokens is going to have a corresponding embedding that is learned through the training process of these static embedding models. Because, as mentioned, we're essentially going to be creating a learned lookup table, where then as we pop in some sequence of text, each of the individual words, or however it's tokenized, are going to be split up, and then all of the pre-computed embeddings are going to be mapped back to those tokens. For the sake of example, we generally look at full words split up as individual tokens, but in general, as we just saw, it can be a little bit more complicated than that. However, creating a fixed vocabulary using something like tokenization is taking first your first corpus of text and converting it all and mapping all of those words using a tokenizer into the actual numbers. We then usually identify all of the unique word tokens, apply some sort of frequency threshold to exclude very rare words, and then often we set some form of maximum vocabulary size. Usually this is around 32,000 or upwards depending on how crazy you want to get. And then different special tokens such as representing out of vocabulary words or other maybe unique Unicode characters are going to be input in. That was a very, very simplified explanation, so I definitely recommend, and we'll be linking in the description below, to watch the greatest to ever do it, Andre Karpathy here, build the GPT tokenizer from scratch. This will certainly help you understand the wacky, wild world of tokenization. But when we're actually inputting a sentence like "we love NLP" back into a static embedding model, it's going to undergo the same tokenization, and then essentially all of the words are going to be mapped back to the vocabulary of this model. So within our vocabulary, we are going to have a corresponding learned vector representation of each one of these words. Now, having the representation of each word is kind of useful, but generally you want to encode sequences of words, which is where we actually start looking into different pooling mechanisms. So with static embeddings, we're not going to do anything too fancy. Generally, the embeddings for each individual word are going to be combined in some way. And there's a few different ways of actually doing that. You may do just a simple averaging approach, or taking the arithmetic mean of all of the word vectors, giving equal weight to each one of those words. But there's also a couple different approaches of applying in different weighted averaging. Techniques like term frequency, inverse document frequency, and smooth inverse frequency are essentially going to look at the frequency of words and give less of an influence to common words and emphasize more distinctive terms. which for an example sentence of something like, I have no interest in hearing about the rising interest rate of the bank, we would give less of an importance to things like of the or about the, and more emphasis on things like interest or bank or no. But with that, let's actually take a look at Word2Vec in action. So I can import Word2Vec using the static vectors package, which is a useful maintained package for working with static embedding models. Then we can go down the line and see, which if you've looked at any major content around embedding models, you'll probably see the example and the common example that I'll be doing. But we can do something like get the embedding for the word king. And so you'll see that king here has now become a large array of numbers. And each one of these numbers is going to represent a learned dimension about the word king. These dimensions can be thought of similar to how you and I might understand dimensions, like we live in a three-dimensional world, but thoughts and ideas and things like the word king have a lot of different dimensions of understanding to them. In our case here, we've captured 300 dimensions of the word king in this vector. And these dimensions can also be thought of almost geometrically as well, as vector representations are considered high dimension representations of these things or ideas. But the intuitive and easy approach here is to think that each one of these dimensions kind of encapsulates a little bit of the nuances of the idea of the word king. So we can see that getting the vector for man, woman, and queen, respectively, gives us some different 300 dimension vector representations. Now, this might be a little bit difficult to wrap your head around, as we literally can only imagine in upwards of 3 dimensions, but what we can do is actually look at how these numbers and dimensions can be used. And the biggest approach and most common one, especially for a lot of AI-related pipelines today, are going to be doing some form of semantic similarity, or based on the semantic dense vector representations that we have output per each one of these different sequences or individual words, we can actually directly and mathematically compare them together. You can think of this literally and very similarly to how you might actually calculate the distance between 2 points on a XY line. Except in this case, we're not looking at 2 dimensions, we're looking at the distance between these points in 300 dimensions. So a little bit more difficult to wrap your head around, but if you want to think about it geometrically, that's kind of what's going on. A very popular thing to do is actually use cosine similarity, which is more going to compare the actual angles between 2 points as they relate to the center. So what we can do is pop in these vectors together and calculate the cosine similarity between them. So we'll see that from our example, queen and king are about 65% similar, man and woman are about 76% similar, king and man are calculated to be about 22% similar, queen and woman at 31, but then king and woman are going to be a little less similar, and queen and man are going to be a little less similar. So you can see how it's kind of picked up on these different ideas and are able to kind of map them back and put the similarity together based on kind of how they've been constructed socially and culturally within human language. Now, one of the more interesting things about vector arithmetic is that because we have representations of words in numbers, we can start to do some pretty interesting things. So I put together a quick visualization in 3 dimensions. So we're actually going to be reducing the dimensionality of these words into 3 so that we can visualize it in the highest amount of dimensions that we understand. And we're going to show the example of taking the vector number of king, subtracting out the vector number of man, and adding in the vector number of woman, and see where it lines up. Spoiler alert. So looking at this 3D chart here, we can see some pretty interesting things. If we look just at our original point of king here, we can see that it's pretty close to prince. And so those things that are close together mean that they tend to be semantically related or semantically similar. So we see things like father and son be very close together, mother and daughter, woman and girl, boy and man. And then going back to our example, we have king here, and subtracting out the vector for man from king puts a point over here. But then interestingly enough, if we take that point and then add in the vector for woman, we get a point here. And what is right close by to queen? That is king minus man plus woman. But now that we have an understanding of static embedding models and how they work and how they're almost like lookup tables that then get pooled together to create one final encoded representation, one of the biggest issues that you might see is that each one of the individual learned embeddings for each of the words are, of course, static, which means that they suffer from this cool word polysemy, or the coexistence of many possible meanings for a word or phrase. What we just went over a little bit ago, showing these different static versus contextual embeddings and transformer-based embedding model diagrams, is that things like I went to the bank, the river bank was muddy, and Bank of America, that word and understanding for bank is quite different across all three of these sentences. But the vector for bank from a static embedding model is going to be the same when ran through the model. That is where things like the transformer models and attention-based models actually shine, because they're able to use their attention mechanism to actually on the fly change the meaning and representation of a word based on the context around it. We can visualize this real quick by looking at the two sentences. I went to the bank to withdraw some money, and we all swam down to the muddy riverbank using one of the models BERT-based uncased, which is just one of the base models that is uncased, meaning that everything is going to be just in flat lowercase from Google. And so running this through the BERT model, what we're going to do is actually visualize the attention mechanism here within our embeddings. We can see that within the attention mechanism that the word bank is being very much so correlated and influenced by this word here, withdraw. That is, of course, going to be in the first sentence. And then in the second sentence, we can see that bank here is being heavily influenced by swam. And so that's why the attention mechanism is able to do these very nuanced contextual embeddings, because it looks at all of the influence of the other words in the sentence here to actually determine its final representation and understanding of a word. And we can see that this is backed up because the similarity between both banks when we do the cosine similarity is only going to be 29%. But if we actually run a different sentence in, like the bank manager approved my loan for the application, and take out the encoding of this bank, it is going to be 0.81 or 81% similar to the original finance-related bank word. But enough talk about transformer-based encodings, we're here to talk about static models. So, as I mentioned earlier, while transformer-based embedding models do have that impressive contextual performance, they come with the major downside of requiring magnitudes more compute to actually do these calculations. This is where it is interesting to actually revisit static embeddings. And while it's unlikely to be able to push the higher end of transformer-based approaches with static embeddings, using some modern techniques, we can train a lot better models. And this was revisited in a major way by Mr. Tom Arson here, who applied some modern techniques and data to create a static embedding model that performed above the BM25 baseline and almost close to some of the performance of things like All-Mini LML6v2. And of course, the biggest thing here is that all of this is able to be performed with incredible speeds of being able to do almost 100,000 queries per second. Now, on top of just having more modern data sets, the biggest innovation is actually using contrastive learning. This is something that we've seen generally used with aligning multimodal representations with things like contrastive language image pre-training models or CLIP models that are able to represent both text and images together in one space. And this is also kind of what's powered the interchangeability and understanding of things like audio, video, and image understanding in language models. What we mean by this is that essentially the learning method is that the embedding model is going to calculate the similarities between pairs or more of text sequences. And the inputs are then going to pass through the model, be encoded into embeddings. We're going to contrast these examples and their similarities together. And over time, we'll try to position more similar things together while pushing away unrelated inputs. This is a little bit easier to understand when looking at a data example. If you look at the original training code, which is in this blog, which I'll of course have linked down in the description below, Tom is using multiple negatives ranking loss, which essentially is going to include one anchor sample, one positive sample, and then multiple negative samples. So given the input of this anchor, as well as the positive and all of the negatives input into the model, we are going to nudge the model towards better positioning the anchor and the positive document together, while pushing away the representation in this high dimension space of these negatives here. The interesting part here is that the harder it is to determine between the positives or the negatives, can actually increase the robustness of the model trained. So using techniques like hard negative mining or things like that to provide very similar yet unrelated examples of the negatives is a great technique to be able to do this learning more effectively. So Tom and the team applied this with some modern data sets to train a fully new static embedding model, as well as using some Matryoshka representation learning, which I've implemented a few times in some of my other videos of fine-tuning sentence embedding models. But what we can do is go ahead and load it and give it a shot. So we can run this right on CPU because it is low parameter account and doesn't take a lot of effort. And let's go ahead and compare these sentences. It is known for its dry red chili powder. It is popular for dried red chili powder, and these monsters will move in large groups. Our expectation is, of course, that these two sentences are going to be similar, and this third will be much more different than the other two. And that we can pretty much see. So looking at this first sentence here, we can see that it is perfectly similar to itself, very similar to the second, and then not quite similar at all to this last one. But the most impressive thing to actually take away from this example that Tom's given us here is that we're able to push the performance of embeddings for common tasks, like things like similarity or retrieval, above classic ranking algorithms like BM25 as a baseline. And we're even getting close to the performance of things like All-Mini LM, which in the given evaluations was just 6 percentage points behind All-Mini LM, coming out to 0.5032 versus 0.5623 respectively. And all on top of this, this allows for upwards of 107,000 sentences per second to be computed on CPU from Tom's experimentation. Well, in similar environments, All-Mini LM can only run about 1,739 per second, so increases of up to 62 times speed. Something like this can be incredibly beneficial for large-scale production settings where a small accuracy trade-off may be worthwhile. And also, additional innovations in static embedding models have been proven to show that we can push this a little step forward. So experimenting and trying things out like this yourself could lead to some innovative breakthroughs. I gave this a shot by just pretty much recreating the training environment, but this time using Modern Burp Base's tokenizer instead of Burp Base on case like the original, and I did manage to put together a quick static embedding model that is going to be linked down below here, but I was only able to push this up to about 0.4791 on the NanoBear normalized discounted cumulative gains at 10 metric, which is a common metric for information retrieval. So I'll be linking to this article. It's certainly worth the read. It goes super in depth into exactly how this was trained with code examples as well. So big shout out to Tom and the team for putting together this work and open sourcing it quite nicely. Certainly worth a read. I'll have it linked in the description below. But the second topic of the day, which we'll cover briefly at the end here, is actually the embedding model distillation process, where rather than relying on actually training a full model from the start, what if we actually took an existing transformer and contextual-based model and converted it into a static embedding model? Well, that's exactly what the aptly named Model 2 Vec package does. Well, there is another blog post that I'll have linked in the description below for you to check out. The high-level overview of how this works is that essentially we're going to take an existing transformer-based embedding model, run every single token in the model's vocabulary through the model, and then store those embeddings alongside the vocabulary. We then go through an optional dimensionality reduction step, so we can change it from whatever amount of dimensions that our original output is and truncate that into a smaller one, and then also weight each embedding based on some power rules. This is a super interesting way of actually approaching that because essentially it's going to bootstrap static embeddings from transformer models by creating that lookup table of vector representations directly. It then also applies the dimensionality reduction and weighting tokens appropriately without kind of requiring any sort of extensive training that we might have seen in some of our examples before. So just to quickly go over these 3 steps, run every token in the model's vocabulary through the model and store the embedding is pretty straightforward, so I won't go into that one. But reducing the dimensionality of the output embedding is going to rely on something called principal component analysis dimensionality reduction, or PCA for short. PCA is a way of taking high dimensional data and mapping it down to, of course, well, lower dimensions here, and is what we use to actually take our 300 dimension representation and change it into 3 dimensions for our visualization that we showed earlier with the king, woman, queen example. Without getting too much into the math, the intuitive way of understanding this is that we're attempting to map the high dimensional data to lower dimensional space while maintaining the geometric distribution of the data as best as possible. So this means that we can take large embeddings and essentially convert them into smaller embeddings with a minimal loss in the actual semantic meanings of these embeddings and their relationships to each other. This has a few different benefits in the entire process here. We can not only store more efficient and smaller vector representations in total in our actual lookup table here, but doing this reduction can help normalize and actually denoise the data from any sort of high dimension model specific information that was learned over the course of the transformer model training. So we can reduce any redundant learnings and also assist in generalizing our static embedding model a little bit more. So while we do lose the specificity of the transformer-based embedding, this will help make the token-specific embeddings more applicable to wider scenarios in this static embedding model. And then hand in hand with this is the 3rd step, which is weighting each of these embeddings. So what I put down here is that when you really consider that a static embedding of a sequence, document, or sentence will simply be that pooled average or some sort of weighted frequency of the individual token level embeddings, it is important to add in some form of individual weighting. This weighting actually happens pretty much automatically when we use attention-based models because we relate words and their meanings more specifically to the semantically rich words that are contextually around them. So without the luxury of attention, we essentially are going to use a simplified version of smooth inverse frequency based on something called Zipf's law, which states that when a list of measured values is sorted in decreasing order, the value of the nth entry is often approximately inversely proportional to n. Or in other words, it is usually found that the most common word occurs approximately twice as often as the next common one, 3 times as often as the 3rd most common, and so on. And the thing that we can really take advantage on is that most vocabularies for these models are already frequency ordered lists. So we can assume that this holds true and effectively downweight frequent words and upweight more rare words, provided the list here. So the Model 2 VEC algorithm applies this 3-step process using a given transformer embedding model and an optional vocabulary to pretty much quickly build these static embedding models based on the inputs. So let's try it out. We're going to be using the Beijing Academy of Artificial Intelligence model, BGE-M3, which is a multilingual embedding model, basically because it is about 560 million parameters. So it's quite a beefy and capable one, and is able of processing sequences of up to 8,192 tokens down into 1,024 dimension vector representations. So what we're going to do is take this model and specify it, and then we're going to do the dimensionality reduction of 256. So just kicking this off, what you're going to see actually happen is the model will be loaded if you don't have it downloaded already, and then it's going to start going through each individual word in its vocabulary and storing the embedding that comes out from the model. So you'll see that my video's gotten a little bit choppy as my CPU is under load. computing these embeddings. So I'll be back in a couple minutes as this finishes up. So once that's gone ahead and finished up, I've saved it just in a quick folder here. Then I'll load the regular model as well as the distilled model onto CPU. And what we're going to do is use a quick anchor, positive, and negative example. So I have this, what is Didier Rueff best known for as a photographer, as well as a provided positive here in the second position and a negative in the third position here. If we run through the embeddings and calculate the similarities for both of the models, what we can see here is something pretty interesting. We see from the base model that our anchor and positive is at a 75% similarity, and our anchor and negative is at a 35% similarity. And then looking at our distilled model of the BGE M3, we see that the anchor and positive is at 0.37, and the anchor and negative is at 0.10. So while our direct computations are a little bit different, the actual expected result of having a higher similarity between the positive and the anchor versus the positive and the negative still holds true in this case. And at the end of it all, we have a nicely distilled down sentence embedding model as a static embedding model that we can use for any sort of downstream task. So to close off our discussion here today, my main kind of point is that while modern-day embedding models based on transformers can create robust dynamic embeddings, applying new data and approaches to old techniques have found static embedding models working their way back into the stack. In this, the latest in research in this area begins to provide a competitive output to some of the most used transformer models, but at a fraction of the parameters and resources required to run, and up to 400 times faster in comparison. So it's a very compelling and interesting thing to keep your eye out on, or even do some experiments yourself with, if interested. With all that being said, hope you learned something interesting today. If you liked the video, like the video. If you have any questions, leave them in the comments below. And if you want to see more like this, consider subscribing. If you want to support the channel further, consider leaving a super thanks or joining a channel membership. Thank you, and have a great day.